very much. Hello, everybody. So my name is. Does it work? Does it do something? Let's see. Yes. It's Marc Hanheide. I'm from the University of Lincoln, and I'm the director of the Center for Autonomous Systems there. We are particularly interested in long-term autonomy. So that means having robots that actually operate for an extended period of time, and I often phrase it as getting better on the job. So we're much interested in temporal representations, and this is one of the bits that I'm going to talk about today when we talk about unsupervised learning for long-term 3D stable objects. Let's have a, just need to get used to this one. There we go. So in this particular work, we are looking at 3D point clouds, getting from 3D LiDAR sensors. And the idea here is that, of course, when you actually work in long term and you're going to have seen an environment at some point in time and you've mapped it out, if you come back later, things may have changed, right? And we know that some objects may probably still be there and some others not. And we all know that if you have created a map and you come back to it and it has changed, that might be quite detrimental to localization in it. And this is part of a European project called Bacchus, where we do this particularly also in vineyards. So there's some extension to this work which has explored this further in vineyards. Probably going to talk a little bit about it at the end. So what we're focusing on here is not this sort of short-term, you have got a car driving to the scene, a person walking while you're mapping. We're talking about these sort of long-term changes that you may not observe. They may happen while you're away, and you still want to kind of take account of them. So particular when we have things in agriculture, which we're very excited about, is that things grow. 90% of the scene is actually going to change because things grow. Actually, I can also say that data sets are pretty rare in this domain. When you look at really long-term change, you want to see how things are happening. So this is why we've done this on the Uni Michigan North Campus long-term data set, which we used for this particular work, but we've got our own in another domain as well. So the idea is we want to capture these dynamic objects as sort of, the problem that happened that you may think, actually, this car is part of the scene. It hasn't moved while I was recording, but we all know they tend to move at some point, right? So ideally, we want to actually find out. So we could do something like semantic segmentation, using large semantic annotation data set and say, like, these things are things that may move, these things are things that may be static. So it's very closely related in that sense to semantic segmentation in 3D point clouds. But we wanted to actually have something that can learn these things rather than us annotating what objects may move, etc. Well, that's the key part. So ideally, I want to kind of detect things like this light post being stable, these cars being unstable, and we really don't want to do a lot of annotation here. So instead, we decided, well, let's go for some sort of long-term data sets where we actually have got different time slices of the same scene and use that in an unsupervised way to learn general shapes of things that move. Simple to say, right? So hypothesis is that we can learn some regression that learns the shape of long-term stable objects by having multiple observations of the environment, and do this in a self-supervised manner, so we don't have to annotate this manually. Okay? So key part here, we get this sort of point cloud in, we have done some sort of slime of an environment. This is all map-based. We have some extension of this work, which is more like actually scan-based. Now here we're focusing on maps, and we kind of learn this filter, and we talk about a regression here. We want to actually have a regression that characterizes on a continuous scale something as very stable and something as very unstable. Okay? So rather than just having a binary switch here, would like to get a sort of idea of how much this thing is going to change part of the scene. Good. So, two main contributions. One is this unsupervised pointwise labeling algorithm I'm going to talk about, and the other one is the actual regression network. And if you've been in the main talk before, you've seen all the many backends you can put onto 3D point clouds. We used PointNet++, but you can actually do RangeNet or whatever, general ideas. The same, and pretty much I can already summarize the architecture. Quite simple, some sort of 3D point-based backend, in this case PointNet++, and then you have the actual regression front end here. All right, so talking about this main part of the unsupervised labeling algorithm to begin with. So we have got a number of scans large-scale maps from different time slices. So when I talk here about K, I'm talking about different times these maps have been created. Same environment, it's different time slices effectively. I remove the ground and remove some outliers, a bit of pre-processing to clear this all out. Then I make sure that I've got them properly globally registered. So we do some kind of general overall registration. In this case, we've done ICP. There's different other approaches. And again, the keynote early on making some reference to some of them. Now we also played around with others, but in our data set, just ICP registration works pretty fine, I would say. And then we get these sort of processed maps that are nicely spatially aligned, but temporally distinct. Then you can go this, basically you do a permutation of all the different maps you've got. You set one as the reference, you take another one, and you compare always which is the closest point that corresponds to this. So basically, while you're doing ICP, you can see which data association you do. This point is the closest to this one, is closest to this one. And you can do this over all time slices, so you get all these sort of associations, and then it tells you that actually some of the points have to actually reach pretty far to match a point in the other map, right? While others are very closely aligned. So it's basically you do ICP to do global registration, and then you do these sort of local associations to identify the distance, the immediate distance effectively of these points. Pretty straightforward, I would say. And then we have got some that have quite far distance and some that have quite small value. That's the distance value. If you do this over all the possible permutations in the map, you get a distance vector for each of those points. So that gives us the sort of labeled maps. For each of these maps, we have got the label 2 against all the other registration maps effectively. In the end, what we want is to do the regression not just on the distance, but we want to do a regression onto an interval of 0 to 1, like, you know, from not stable to very stable. Oops, that was too quick. And so just to kind of bound it in this nice interval, we use this function effectively, and the max is the maximum distance that we find in this vector of distances. So we always take those away. If something has moved very far, though, in one of those maps, we consider that as the maximum. You can experiment with mean or something like this as well. In here, median, we've tried this so far. The maximum seems to be working fine for us. Cool. So that gives us these labeled maps. Yeah, we have got now for each of these environments. We can do this, of course, in different environments. You have these temporary labeled maps. Effectively, now you have the real point cloud, and you've got a labeled point cloud where each of the points is labeled with a value of 0 to 1. Okay. And then we basically, as I said before, relatively simple architecture. So an autoencoder type of thing, and now we get this in the end of this. So refer to the paper to read the exact details about the architecture here if you want. But the principle is, pretty much straightforward. We then, in the end, get a pointwise stability score for it. Okay. So, and also the loss function is relatively straightforward. Just root mean square error. Okay. So, what does it give us now? Right? We can train this, and we can train this on various data sets, and we don't have to do any specific annotation. All we need is data sets that have different time slices of the same environment that we can register on top of each other. The rest then works pretty much automatically. So as I said, in this work we've used the North Campus long-term data set. It has, for those who don't know, this is basically on, obviously, University of Michigan North Campus. They have been driving around similar routes on different, 27 recordings over a 15-month period. So you've got things like seasonal change in there, and of course you've got also these things that are, cars, etc., that sometimes are there, sometimes are not there. You may even have changes in terms of buildings that appear and do disappear, containers and those sort of things in there. So it's a really, really valuable data set. You don't get huge amounts of data, let's say, for every instance you see in there, right? But you get a good gist of sort of long-term changes in there. And that's what we're really interested in. So you get a bit of so we took, in this case, 2 distinct areas, which we looked into further detail, because the rest is just a lot of just trees and house fronts. There was not much to be seen. So we took these two areas from this data set, generated the maps for them, did some slam on the data set here, generated maps for all the different time slices. So every time this recording car went through them, we did the recording and built the maps and fed them through. And then you get this sort of annotation. So this is from our labeling. So we see actually, because of the temporal aspect for this area, we see some of the bits that are blue are considered more stable. So where the correspondence of the auto labeling found actually, oh yeah, this point was existing in all the images we've looked at, while the more red ones were actually absent in some of them. Yeah, so that's the sort of interestingly, you see the sort of stuff on trees, for instance, right? Trees are mostly stable, but some parts they seem to have changed a little bit. Here, this one was quite noisy. We always get these sort of nice pole structures that seem to be fairly stable in this auto labeling that we get there. You see, so vegetation is not necessarily the best feature, but you know, it's better than relying on cars, for instance, when it comes to stability. Okay, so first then we try to see how well this works, right? How well can we actually, how well does our regression work? We learned our regression, we have some ground truth in this case being our label set. So we've just learned this, trained this on some of the time slices and then tested it on some of the others. And that is an indication that the regression network actually performs pretty well. So we have got our labeling is kind of useful. Then also our regression network actually has a very good performance. With the disclaimer that, of course, this is in the same environment, different time slices, but same environment. So, you know, next step is also, we're currently working as a generalization into completely unseen environments. There is some generalization between the areas. That's already what we have studied so far. So we've got these two completely distinct areas, and we kept them separate, where we've got one test that we trained on area 1 and one which we trained on area 2, and they are quite different. You know, the resolution, the size, and all this stuff is quite different in that sense. The distance from which you have seen in different aspects here is quite a bit varied, but they have got the sort of same type of objects in them, right? That's my disclaimer for now. But of course, they both feature some pole structures, some car structures, etc. But we've now worked this also in vineyards, in agriculture domains. And it also works there fairly well, where you actually where it then learns over time that you shouldn't rely really too much on this, on the plants, right? They change massively. On day one, if you're looking into vines, actually they are just a stick in the early spring of the ground, and then towards the end of the season they are a massive bush. That's a massive change. You don't want to use that if you want to localize anything, right? So that's we use this approach into it forward. So generally, so we've done this against some relatively simple baseline that was just a binary segmentation, semantic segmentation here. We compared this with, and we used the intersection over unions, the mean of that to compare. And what we see is, you know, the generalization capability is what our approach was particularly good at. So we have been able to say when it was trained on area 1, then actually the baseline also does a pretty good job, so in often cases better than ours. But when we go from a model that has been trained in area 1, we can do much better generalization here. Yeah? So we go from area 1 on which, something that has been trained on area 1, tested in area 2, we get a much better performance generalization. The same if we something that's trained on area 2 but tested in area 1, we get a much better performance there. So that gives us an indication that with this automatic labeling and the regression network we've trained, we can actually go, and we have learned the general structures of objects that have that are the actual shape and the actual appearance of these objects that tend to move. This is, in our case, most often things like cars, things like bicycles, things like other, actually moving objects, and to some extent also parts of vegetation. And if you look into the details here, what has been, what has been shown to be mainly dynamic here, we see that it is clearly these sort of, in this case, mainly the car structures, plus some of the vegetation bits here, and similarly here. Right? So we have got, now we can use this to filter out these objects, for instance, for localization. We can even filter them out at the mapping stage already, because we know these are things that may actually change. So we don't now need to go back and have long-term data sets. We can use the model, use it as a kind of filter of maps if you want, and use this trained system here to actually clean out maps from objects that we have previously trained tend to be dynamic. Or we may actually have a particular interest in them and filter them out in the other direction. All right, good. So the key part here is that we have got this unsupervised labeling algorithm. You just need a sort of long-term data set. You register the point clouds and then you feed it through the system. It generates labels automatically. Then we have got this LTS network that can do this for unseen point clouds. So you have a point cloud maps that we haven't seen. You filter it through and it gives you an indication of which part of the scene are most likely stable, which ones are most likely dynamic, that you can expect to change also into the future. We've shown this as quite an effective way to identify these sort of long-term stable objects, and currently we are working on a sort of long-term data set in vineyards, which we have published as well. We have extended this to actually do it not only on maps but on direct scans, so you can directly filter your scans if you're actually going out and deploy this, so you basically ignore the things that you know you shouldn't rely on anyway. They're unlikely to be in the map, for instance. And we have also current work that we're working on with colleagues in the University of Bonn on adapting classical moving object segmentation, which normally looks at the short-term frames. You've got a couple of frames where objects are moving and you're trying to segment those out. We're trying to extend those methods into the really long-term as a sort of alternative approach from what we've been discussing here. That's where I shall end. This is almost exclusively work by my PhD student Ibrahim, who couldn't make it here due to visa issues. So very sorry you have to actually put up with me today, but he's done most of the work, so all the gratitude to him. And if you want to know more about what we're doing, it's down there. Thank you.